Welcome again to the course on audio signal processing for music applications. This week we're talking about the sinusoidal model. And in the previous theory lecture we presented the actual model and a little bit about how these sinusoids can be visualized in the spectral domain. So let's continue with that. We will first overview a little bit the model and then focus on the idea of detecting peaks in the spectral domain, which are going to be our sinusoids. And also we're going to be talking about how to track them in time. So these sine waves vary in time in a particular sound. So how can we track these time varying sine waves in a spectrogram? So the sine model is simple. It's a sum of time varying sinusoids. And in the previous class, we made emphasis on this idea that we need to detect these sinusoids in the frequency domain. Therefore, we need to choose a window size that is good enough to be able to isolate those sinusoids, or at least be able to visually have separate peaks for these sinusoids. Okay, in this particular case, these two sinusoids, 440 and 490, we need a window size of 5,291 samples in order for being able to have these two main lobes separate. But how do we measure the values of the sinusoids in the spectrum? Well, if we choose the window size correctly, as we showed, we will have a peak for every sinusoid in the signal. Then, to measure the frequency and amplitude of each sinusoid, we have to just find the tip of the peak and its height. So we defined a peak as the location in the magnitude spectrum. So P sub r, the peak, is going to be the magnitude spectrum at the location K sub 0 when the previous location, so the location of the spectrum when K sub 0 minus 1 is smaller, and the next location, so the location at K sub 0 plus 1, is also smaller. So that's going to be what we call a local maximum. So in this plot, we see a local maxima for the different peaks. Okay, so the crosses, the blue crosses, are local maxima. And also in the phase spectrum, what we basically do is just read the location of these local maxima in the phase spectrum. So we have, with this procedure, we have the location of the peak, which is going to be K sub 0. Then we have the magnitude, which is going to be mx of K sub 0. And we have the phase, which is going to be px of K sub 0. But there's a little problem. In fact, you can visually may identify this problem. There is not enough resolution. So one solution to this resolution problem is to do zero padding. We use an FFT size much larger than the window size, and we have been talking about that. So for example, in this particular example, we have increased the FFT size of the previous example by 2. The window size was the same, but we added 0 to the n up to the next power of 2. And this results into a much smoother spectrum. And now the local maxima, computed in the same way, so these blue crosses, are much better. They are located visually you can see that they are located in a better place. They are located in a place that looks like it's more the center of the peak, and therefore the magnitude and the phase will be better. But if we want a good enough resolution, we will need to increase the FFT size a lot, and that will be quite computationally expensive. So is there any other solution? Well, yes. We can do a cheaper interpolation by using, for example, parabolic interpolation. The parabola is a function with a shape quite similar to the tip of the lobe of the spectrum of the analysis window in the dB scale. So this is the equation of a parabola, where P is the center of the parabola, A is the concavity measure, and B is the offset. And this is a sampled version of the parabola. So we have the different values n. And so this is very similar to what we would see as a sampled function. Okay. So to perform a parabolic interpolation on a spectral peak, we can just use the three highest values of the magnitude of the peak. For example, in this case, the k minus 1, k, and k plus 1 locations of the mx spectrum can be considered to be the three highest values of a parabola. So the x minus 1, x0, and x1. And then we can apply the equation of the parabola in a way to find where would be the center of this parabola. And the center of the parabola will be defined by this equation in which k sub p, which will be the kind of the frequency or the location of the center, would be equal to this k, that was the highest point, plus these values, which is going to be the previous and the next values, and compute it in this way. And then it's going to be very easy to read what would be the amplitude of this value. So we can basically plug in the interpolated k sub p into the parabolic equation and obtain the amplitude, the height of this peak. Okay, so with this equation, basically we can refine the peak positions, and we can combine it with the zero padding, so to get a much better result. So this example is exactly that. There is some parabolic interpolation together with some zero padding. And if you would zoom into this, you would see that this is quite a bit better than the two previous examples, the one without any zero padding or the one with just zero padding. So this will give us quite a good measure of frequency, amplitude, and phase of all the sinusoids present in a spectrum. So we will get these. So we'll get a value of the frequency location of a peak, k sub p, and it will be computed with this equation. Then we can convert this k into hertz, into frequency, by multiplying by the sampling rate and divided by n. Then we can compute the amplitude by using this parabolic idea. And finally, the phase will be very straightforward. We can just read the phase of that location, and this doesn't even have to have any interpolation. By just reading the closest, that should be enough. But these are the values of a single frame, and the sinusoidal model is about time-varying sounds. So time-varying sinusoids. So how do we go about that? So we have to deal with spectrograms and find time-varying sinusoids. And we will define a time-varying sinusoid as a stable peak track in the spectrogram. So this variability will be constrained, and we will define sort of peaks that evolve in time, that sort of move in time, but not so much. And this stability will be measured by the frequency and amplitude of successive frames. We could also look at the phase derivative in time frequency for that. In practice, we are going to just focus on the frequency and amplitude variability, but the phase is also a very interesting value to look at. So the condition for a peak of a frame to be part of a track is defined by this equation. So a peak, a particular frequency of a peak, f sub p, of a given frame, L, will be part of a track if the distance between that frequency and the frequency of the previous frame, so the track is coming from from the previous frame if the absolute value of this difference is smaller than a threshold. And also if it exists a track for a certain amount of time. So we will be making a constraint in terms of the frequency, in terms of that it doesn't change that much, and at the same time we will make it a constraint in terms of how long has this track been in existence. If it's too short, it means it's like a short burst, and that's not really a sinusoid. So this is an example of tracking these sine waves in a sound, in a bendir. Bendir is a drum used in Turkey and several other places. So this is a non-harmonic sound. So it's a sound that is quite complex, but it has partials, it has sinusoids, and we can track them. So with this algorithm, these black lines correspond to the tracking. But let's hear the bendir first. Okay, so it's an instrument that doesn't have a clear pitch, and therefore the tracks are a little bit kind of very unstable, and they keep changing and appearing and disappearing. So this is what we would find. And also we can look at the same tracks in the phase spectrum. So if we take the phase spectrogram, which is the derivative of the phase, and we plot those black lines, the frequency tracks on top of that, we get this result. And it's quite interesting because clearly we see that the black tracks are in the places where the color is clear, and these are the locations where the phases changes less, where there is more phase continuity. So this indicates that also the phase information would be quite relevant in tracking these sinusoids, because the phase information allows us to distinguish this variability stability aspect of a given partial. So sorry, there are not that many references on these topics. So apart from the Wikipedia entry for sinusoidal model, or of course Julius Smith's discussion on all this spectral analysis on his online book. And that's basically it. So this is all for this lecture. We have presented the sinusoidal model, sound representation built on top of the short-time Fourier transform, that reduces the amount of information and that get rid of non-relevant spectral components. However, its use for the analysis of sound is not as easy as the use of the STFT. We have to understand a bit more about spectra and about windows in order to make good use of this model. Hopefully by now you're starting to get a grasp on that. Now we have to complete the explanation of the sinusoidal model by describing the synthesis part. And this is what we'll be doing in the next lecture. So I hope to see you then. Bye-bye.